Welcome back to Math 451. Today we're going to take a look at numbering systems, where they came from, problems that were associated with them, and how this led to the need for more automated computation systems. So we'll spend a little time in history before we try to face numeric systems that we use today. First, let's look at the ancient numbering systems. The most ancient numbering systems were just a series of tick marks, whether it was counting things in a cave and inscribing tick marks on a wall, or whether it was someone carrying a certain number of tokens that would represent possessions, or might even represent some kind of a trade that was being agreed to between two neighboring societies or two neighboring individuals. These very old systems were too cumbersome. It wouldn't take long to get frustrated with keeping track of 50 or 100 or 150 goats using that many tick marks. So ancient societies realized they had a need to group some of these marks together, say in groups of 5 or 10 or 100, in order to have a more compact numbering systems. So here's the way the Chinese did it. This is one of the oldest numeric systems that exists. It consisted of vertical and horizontal bars. You'll notice that the first 5 numbers are very traditional to that very ancient tick mark approach, but horizontal bars start getting used to denote groups of 5 or perhaps groups of 10, depending on their context. Placement started to matter. Where you actually put these marks would change the role that that mark made, as you can see here on the Chinese systems. The Babylonians, who inherited their system from even older societies in the Mesopotamian area, used 2 symbols as well. They used what looks kind of like a Y with a bar over it to represent a unit. And just like the Chinese system, if you group them together, if you have 2 or 3 or 4 of them, it just simply increments that number of units. In the case of the Mesopotamian society, they created a new symbol for 10, so that you could more conveniently represent numbers between 10 and up to 50. Their system, as you see here, was base 60, involving 59 unique representations of these 2 symbols. They didn't have a concept for 0 being an actual number. They understood nothingness or absence of something, but they didn't view it as a mathematical tool that needed to have a symbol associated with it, which gave them a little bit of problems. In particular, even though they learned how to add and subtract and multiply using these numbers, they couldn't come up with a notion for long division, which may be why they created the base 60 system to begin with, because it breaks so neatly into various groups. You can take 60 and break it into 2 groups, or 3, or 4, or 5, or 10, or 12, or 15, or 20, or 30. But that's a nice, rich list of ways to divide a set of numbers into integer groups. The Mayans had a placeholder system as well in what was a base 20 system. Actually, to be honest, the Mayans had more than one system, depending if it was for business use or religious use. But here we have their base 20 system with some examples of various multiplication operators that they would define. Nevertheless, as you can see, that could get complicated and hard to learn, as you needed more diversity in your multiplication. The Egyptians managed to move forward into the idea of powers. And here we have symbols that they would be familiar with that represented powers of 10. I think the Romans actually went backwards a little bit, because even though they may have had symbols that collected numbers together, as you see there, it became virtually impossible to do arithmetic. Well, you could add, okay, but just try taking a number like 507 times 23 and do it in Roman numerals. That would be immensely awkward, even to the point that a British mathematician in the 10th century was willing to say that there's no practical use for any number greater than the number 9,000. It was complicated, just to say the least. Finally, the last numeral system I'm going to share with you is one that could be used effectively on the field if you're trying to signal to someone else. And we have a numbering system that does have a somewhat of a tens base to it. But again, when you get up to the number 9,000, it somewhat gives out. And perhaps maybe this is the reason why our British mathematician thought that the number 9,000 was about as high as you'd want to go. You can certainly see here the risk of miscommunicating with somebody could be a bit of a problem. Now, when it comes to math tools, the abacus, which was developed in the Eastern cultures, was promoted in the West even by Pope Sylvester nearing the year 1000. And he was viewed with suspicion because addition and other arithmetic on an abacus was so fast compared to what they were using, they thought it really couldn't be of any earthly origin. So there's a certain degree of superstition there that got in the way with the development of mathematics. And then you finally end up coming to the 19th century, where a individual named Charles Babbage borrowed from an idea from a prior century, meaning the later 1700s, that an engine could actually be built that would do arithmetic. Now, he was actually given a grant by the British government of £1,700 to build this thing, and he took the design from his predecessor and said he could do it, but as with a lot of R&D projects, it takes more money than you anticipate, and he had to continue to ask for more until the sum got up to £17,000, and the British government was tired of it and canceled the project. Just like a good engineer, though, he had learned from his mistakes on this and created another machine. I think he called it the analytic engine. And finally, they came up with a difference engine 3, which eventually was built. Whole numbers are going to be just like what they sound like. They represent whole units. So you can have 1, 2, 3, 4, and so forth representing a number. And you could even have negative versions of those that are below 0. And in today's world, we like to think of 0 as a number of itself, neither positive nor negative, but the dividing point between positive and negatives. Now, this is going to be a bit abstract, but it's important for the rest of the class, and that is that these numbers are not the same thing as their symbol representation. It doesn't matter if you use the Mayan approach or the Chinese approach or the Babylonian approach or the Roman approach. They are the same numbers, just written down in different ways. But how we describe them, the numbering system that we'll use is going to affect greatly our ability to do computational mathematics. So the first part about the whole numbers as we view them today is that we can break them up into either positive or negative groups, or we could break them into even or odd groups. Well, there might be other divisions that we would be interested in, but those two are going to be particularly important. Positive and negative numbers, and even and odd numbers. When it comes to even and odd numbers, we can write down an expression that helps us distinguish between the two. If n is any whole number and you multiply it by 2, you're going to get a description of any even number. And if you take an even number and add 1 to it, in other words, make 2n plus 1, that will be a definition of any odd number. So as we continue investigating our numbering systems, let's learn from our brethren from the past, and that is that groupings is necessary. Without groupings of numbers, you end up with an impossibly cluttered numbering system. In today's world, we use base 10. We're used to it. We've learned it from grade school. You almost can't think outside it, but there really isn't anything special about base 10. You could have that base 20 or base 60, as we saw in the past, that could work equally well. But nevertheless, this is how we do it. If you want to take some number, some whole number, that we are now going to call a decimal number, and you want to express it in terms of these groupings, we would say, for example, that 2,631 is nothing more than 2 groups of 1,000 plus 6 groups of 100 plus 3 groups of 10 plus one group of 1. Or, more conveniently, as we'll see later, we could say it's 2 times 10 cubed plus 6 times 10 squared plus 3 times 10 to the first plus 1 times 10 to the 0. Now, if you don't like base 10, maybe you want to go to something like base 8. Now, I've said there computers prefer different bases, such as base 8. Really, they work in base 2, which we'll get to in just a minute. But if you were sitting in base 8, you could write the number 2, 6, 3, 1 as groups of 8, just like we have done below. But that would not represent the same whole number as 2, 6, 3, 1 did in base 10. Those are completely different whole numbers described in different bases. Or we could go to base 2, the way a computer would like to think, and we could do the same thing. We could break this into groups of 2 and write, as you see here, the 101, 110 in terms of these summations of powers of 2. Now, one thing you should notice, as we've just developed these 3 examples, is in base 10, we need exactly 10 symbols from 0 to 9. And in base 8, we need exactly 8 symbols from 0 to 7. And in base 2, we can only use 0 and 1. The physical nature of a computer drives a base 2 numeric system, which is why we're interested in the third bullet there at the bottom. So let's go beyond integers for a moment. Are integers enough? Well, it really doesn't take too long before you realize that you may need to divide whole quantities into portions, like a pie. If you're breaking a pie into 8 pieces to share with a friend, you need the concept of 1 divided by 8, or we would call it 1/8 of a slice of pie. There's any kind of fractions you could create. You can divide a whole number into 5 groups or into 10 groups, and then decide how many of those groups that you're interested in using. The fractional ratio, the way we define it, and which becomes what we call the rational numbers, is always the ratio of 2 integers. You can see in my example where I have 3 over 5 as a rational number, or 8 in 10 as a rational number. We could generalize that and just call it P over Q, or P out of Q parts, both P and Q being integers. Now, you might complain a bit about that 8/10, and you could say, wait, I could have just as easily broken it into 5 units and said that was 4/5. And that would be, in fact, the case. And that leads us to what we would call a reduced fraction, one in which that you cannot simplify it any further. And then we could also define something called a proper fraction, in which the numerator was less than the denominator. But there's really nothing particularly improper about a fraction where P is greater than Q. Sometimes it's nice to define that when we're doing various proofs, which we will be doing shortly. One thing that's kind of interesting, if you do limit yourself to proper fractions, is that either P, the numerator, or Q, the denominator, must be odd. Now, that's kind of interesting. Is that really true? Why couldn't you have a P over Q that involved both even numbers and still be reduced to the lowest possible form? Think about that for a little bit, and we will be coming back to that question next time when we start to introduce the idea of numbers that are neither whole numbers nor ratios or rational numbers. And with that, let's go ahead and end this session. We'll pick it up here when we move on to irrational numbers next time.